welcome to another video on control systems. In this video, we'll do a recap of Routh's array, Routh locus, and if possible, we'll do Bode plots and polar plots. Otherwise, we'll move on to the next video in which we'll be discussing Bode and polar plots. Before we proceed, these are the things we should be knowing. Okay, in the recap, so let us try to have some questions and start answering them to understand the need of all these topics. So first and foremost thing, let us start with what is the requirement to have a Routh array. So what is required to write a Routh array. So what is required to write Routh arrays? So we need, so if it is required to have the characteristic equation of the system, meaning I should know what is del of s. So del of s is nothing but 1 plus g of s into h of s equal to 0, meaning what is required is, even if you have the open loop transfer function, which is nothing but g of s into h of s for a unity feedback system. If you have this g of s into h of s, assume that it is something like into s plus 3, s plus 4. If you know the open loop transfer function of a system, then it is sufficient to write the Routh array. If you know this, so how do I get 1 plus g of s into h of s equal to 0? You just make this g of s into h of s, make this plus 1 and equal to 0. Meaning, you take this equation a by s into s plus 3, s plus 4 and plus 1 equal to 0. So this is what is g of s into h of s plus 1 1. So you take the LCM now. So what is LCM? A by s into s plus 3, s plus 4. Since there is nothing here, so it will become s into s plus 3, s plus 4 equal to 0. Since this is equal to 0, so this will become s plus, this will become a plus s into s plus 3, s plus 4 equal to 0. So this happens to be our LFS. So what is required to write the Routh array is, it is required to have the characteristic equation system which can be derived out of open loop transfer function. So if you have the open loop transfer function, it is enough to write the Routh array. Right? Okay. Second question is what is the use of Routh array? So why do you need this Routh array? So Routh array will okay, Routh array will provide information regarding number of closed loop poles to the right hand side of S-plane. Poles of the system. So Routh array will provide information regarding number of closed loop poles of the system towards the right hand side of the S-plane. So what does this actually mean? So if you know the number of poles towards the right hand side of the S-plane, closed loop poles towards the right hand side of the S-plane, then we can talk about stability system. So indirectly, It provides, it gives information information regarding stability of the system. It actually gives the information regarding the stability of the system. So how do you get to know the stability system? If one pole lies to the right hand side of the system is unstable. If two lies onto the right hand side of the plane, it is unstable. And okay, along with this closed loop poles onto the right hand side, it also provides information information regarding the closed closed loop loop poles on the imaginary axis imaginary axis, as well as the root locus gain the root locus gain gain at which system system is oscillatory. You know, anyhow, it will give the how many number of closed loop poles onto the right hand side. That is one information. It also provides the information regarding the stabilizer system, and it also provides the information regarding the closed loop poles on the imaginary axis, as well as it also provides the information regarding root locus gain at which system is oscillatory. So we will going to find a margin, no? So that's what is the value of system, or the root locus gain when the system is oscillatory. So these are the three major information does a root survey will going to provide you regarding the system. Okay, then how does does the root array helps in knowing the stability of the system? How does this will help in, how does the rows array helps in knowing the stability of the system? So how it helps is, once you write the rows array, of course we know how you have to have so many rows of the rows array. Look at the first column of the rows array. If there are no sign change, assume that it is plus, 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 plus. No sign change, system is stable. Assume that there is one negative here, plus, minus, plus, plus, plus. So there are two sign changes. So two sign changes. So these two sign changes indicates two closed loop poles lie on to right hand side of the plane, meaning system is unstable. This is unstable. If there are no sign changes, all the closed loop poles are there onto the left hand side of the plane. That's about. And how do you know the oscillatory system? Oscillatory system, how do you get to know? Oscillatory system can be obtained, or information about the oscillatory system can be known by having auxiliary equation. When you have the auxiliary equation, that is AFS, which is a even polynomial, this auxiliary equation will tell you whether the system is oscillatory. When the system is oscillatory, you will certainly enter the auxiliary equation. So This will talk about the oscillatory system. It also talks about what is the value of k at which system is oscillating. System is oscillating, and it also talks about what frequency system oscillates, which is nothing but omega. So you're going to get k margin from the Routh survey. From A of S, you'll get to know what is the frequency at which you're going to oscillate. So that's about how does the Routh survey help means. Okay, number of sign changes will indicate. Okay, this is our third question. So is our next you can uh, why the order of the auxiliary equation is always polynomial. Why is order of auxiliary equation is always polynomial? Poly, always say even polynomial. Sorry, even. So there's a question: why the order of the auxiliary equation is always a even polynomial? Usually we know that if a system is oscillatory, we'll end up with the auxiliary equation. It is one of the possibilities. So how many poles are there? So 2 is even number. Suppose that you have 4 poles over here. So then it is 4. So this 4 is also even number. Assume that auxiliary equation may also result in something like this poles. Okay. See, now we have fourth order of your auxiliary equation. 2 on imaginary axis, 2 on real axis. Here also this is 4. These are the possibilities of the auxiliary equation. And you may have a special case where you may have repeating poles over here. So can you see the repeating poles? Now this is also of order 4. See, this is 4, this is 2, this is 4, this is 4. All are of even polynomial. So you will never end up with auxiliary equation with odd polynomial. So these are the possible cases of the roots of the auxiliary equation. Roots of the auxiliary equation. Next. Okay, now. So next is this was our fourth question. Okay, while writing the array, so while while writing the Routh's array, if first element of a row is 0 and at least one one element of the other terms of the same row is non-zero. What to do? Meaning, assume that you have some rows have been written. Assume that you end up with something like a 0. This is 8 and then 0, something like this. Suppose you end up with this. In such case, what you do? In such case, you have to replace s by 1 over z and rewrite the rewrite the del of s. Rewrite the del of s and form new rows. New rows. Whenever you end up with this is an example. This is a non-zero quantity. So assume that you have something like this 0, 8, 0, 0, 0 or 0 some x value. So this is that non-zero value. If you end up with this, you have to replace s by 1 over z in the characteristic equation, form the new del of z, write the Routh array for z. for n, z for n minus 1, so on, so z for 0. So they should go till here. You'll get. And of course, you'll not come across the same situation where you'll have this. So this will be eliminated. Then this is our fifth question. What is sixth question? Sixth question is if all elements of a row in a Routh array is 0, assume that you end up with a situation where you end up with a situation you have some terms here, you are just running down here, and then you end up with this 0 0 0 0, all terms are 0. When all terms are 0, you cannot continue, because if you continue this way, this will become infinity, and you cannot continue that. In such case, what to do? You have to eliminate this. You have to eliminate this by taking a row above this. So that's what we call it as auxiliary equation. We'll write an auxiliary equation, which is nothing but this is the auxiliary equation, and you take the derivative of the auxiliary equation respect to s, and write this derivative of coefficients of that s onto these zeros. So then you continue the array. So then you'll never end up with this infinite. So you should complete the Routh array by taking the auxiliary equation a row above that zeroth row. A row above that zeroth row, write the auxiliary equation, write its derivative with respect to differentiate with respect to s, and write the coefficients of the derivatives of AFS over here. Then you continue the array, and later you see what is the change in the first sign in the first column, and then you look at the root of AFS to decide the stability of the system. Yeah. So what next? Uh, how do we get to know if there is only one pole to the right hand of this thing? So how do we get to know? So this is the seventh question. How to know if only one closed loop line to the right hand side of S plane? You can assume that when you have a transfer function, you don't end up with S power n minus 1, power n minus 2. This goes like that. This is S power n, finally it is S power 0. So I'll just start with these, filling these elements, and then continue here. Assume that if the last element becomes something like minus x, and then 0 0 0. So whenever you have this minus x, so this indicates, assume that all these are positive. All these are positive. This is plus, 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 all are plus, except the last one. If you can see here, no sign change, no sign change, no sign change, no sign change, only one sign change. So this is one sign change, meaning that only one closed loop pole lie to the right hand side of the square. So only one is lying here. We don't know. Okay, it may be here, it may be here. It has to be on the real axis. Then all other remaining poles are there on the left hand side of the square. So a negative sign in the last uh, row's first column element, if it is negative, then it is the indication that only one pole lying to the right hand side of the square. Okay, this is about Routh array. Let us find some root locus. So what is this root locus? Root locus is nothing but it's a curve, a curve joining all closed loop positions of a system as the root locus gain as the root locus gain changes from k equal to 0 to k less than infinity. It's a curve joining all closed loop pole positions of a system as the root locus gain k changes from greater than 0 to less than infinity. Meaning, of course, this is GFS into HFS. In this open loop transfer function, you won't have A. This is S into S plus 6, S plus 9. Now, this is what is uh, open loop transfer function. We know that closed loop transfer function of this would be K by S into S plus 6 into S plus 9 plus K. Now the value of K starts from, okay, this is 0 less than, this is K greater than 0 and K less than infinity. For different points of K, the pole positions changes. So loop poles were there at 0, minus 6 and minus 9. This is when K is equal to 0. When K is greater than 0, they are going to change the position. So when they change the position, we know that it goes like this, breaks somewhere here, it goes like this, it just keep moving. So why it is keep moving? As you increase the value of K greater than 0, the closed loop pole starts moving. Here also it starts moving, it just goes here. So this is called as root locus. This is called as root loci. Loci means it is one of the root locus. This is root loci, this is another root loci, this is third root loci. So this is overall thing is called as root locus. Because as it is said, it is the curve traced by, it is the path traced by the curve of the closed loop pole as the value of K goes from greater than 0 to less than infinity. Next, so what is required? Okay, now it is question number, this is 8, this is 9. What is required? Requirement to draw root locus. What is required is you require open loop transfer function with a which is a variable starting from greater than 0 to less than 20. So it can have any number of zeros and any number of ports. So they should have a term k and some position, and you need to have a pole zero form of transformation of open loop transformation. When I say pole zero form, it should be something like k into s plus 3, s plus 2, s into s plus 1, s plus 6, something like this. You can see now this is pole zero form of the transformation. If you know this, you can proceed. What else? Which part of real axis of S plane is a part of root locus. Of course, which you all know very well. Suppose if I have this as my root locus, okay, poles and zeros of a certain Now I want to know which part of the locus real axis of the S-plane is a part of the locus. Now this is not a part. This is a part because in this segment the number of poles plus zeros on the real axis is 1, that is odd number. This is not a part of root locus, and this is again a part of root locus because on real axis you have odd number. So poles will leave from open loop pole, the poles will leave from here and enter into the zero position. And of course we know that when you have complex poles, you're going to have angle of departure. So this is angle of departure is required when you have a complex pole. Okay, putting that aside, which part of real axis of S-plane is a part of locus is that segment which has got even number of odd number of poles plus zeros on real axis towards the right of it, the right of it. So that part will be a part of root locus. Root loci will start or will leave pole position or open loop position and enter open loop zero position. You can see it is leaving here and it goes to the open loop zero. Open loop zero. So this is question number 10. So what is 11th question you can think of? Okay, what is the use of root locus? What is the use of root locus? It gives a visual representation of closed loop position as the k value lies between 0 and infinity. Hence it can be seen whether the poles, the closed loop poles are onto RHS or LHS of the S-plane. Meaning, assume that this is uh, this is how particular testing is there. So assume that this will end up with something like this. This will go here and they will break somewhere here, and then there is some asymptote. It actually goes like this. Assume that it will go. So what is that information you are getting to know? So this is right hand side, this is left hand side of this plane. You got to know that as the value of k increases beyond 0 till infinity, the roots are going this way. So this is a pictorial representation or a graphical representation of closed loop pole position on S-plane regarding their position. So since all the poles are there onto the what left hand side of the S-plane, system is said to be stable. So that's what is the use. And if at all, if there is a conditionally stable system, assume that you have something like this, so then this is going this way and this is breaking and then going like this. So this will tell us for what value of k system will become oscillatory, and beyond which, for what value of k system is stable, and okay, for what values of k system is unstable. So that is, we got k margin. Okay, to write root locus, we need to use Routh's array to find this k margin and the frequency at which this is going to oscillate, minus plus or minus j omega. So with the help of Routh array, we will write the root locus, and it will talk about system stability, whether it is stable, whether it is conditionally stable. So let us see what is an absolutely stable system. So when do we say a system is absolutely stable? System stability. First, it is absolutely stable. So for any values of k between 0 and infinity, the closed loop poles, closed loop poles always line to left hand side of the spline. Then you say it's absolutely stable. When you say it is absolutely unstable, for a value of k greater than 0, a value of k just greater than 0, if closed loop poles line to right hand side of the spline, then system is said to be absolutely unstable. Any value of k slightly greater than 0, the system is having closed loop poles onto the right hand side. Even if it is 1, system is said to be unstable. Third one, let make it equal to 0 also. Now, what is conditionally stable system? Conditionally stable system. So whenever I'm changing the value of k from greater than 0 and less than infinity, for a certain range of k, poles are there on left hand side. For a certain range of k, poles are there at the right hand side. So system goes from stable to unstable. System goes from stable to unstable. Then we say system is conditionally stable. Also true that system can be initially unstable, system may become stable. So both are conditionally stable system. See? So we can think of something like this. So assume that it is, so you may end up with a situation where it is like this. So this is first category. Initially it is stable, and then for larger values it will become unstable. Let us see when does this will occur. So assume that you have something like this. So you have this, and assume that you have this and this. So then, so what will happen is, so now you will have this here and this here, and there is a asymptote which is on this side. For lesser values of k, system is here unstable, and then it becomes stable. Becomes stable. This is for this category. For lesser values of k, system is unstable. Larger values of k, system is stable. System is stable. So this is also under conditionally stable. This is also under conditionally stable system. So we have seen absolutely stable. Okay, absolutely stable, you can just think of like this. There are two poles here. It will just be something like this. It just goes like this. This is always over here. This is conditionally unstable. You can see here. Suppose you are having something like this. So assume that this is here and this is over here. What will happen? It will, it actually goes like this. see system is first just base. Same point. Can you see system is at least having one pole always towards the right hand side. This is conditionally, sorry, this is absolutely unstable system. This is absolutely unstable. This is absolutely stable. This is conditionally stable. So here this is conditionally stable. This is also conditionally stable. Okay. So then the situation may arise where you end up with, when you want to know the angle of departure, angle of arrival. So angle of departure and in Routh locus. So when you need this, assume that you have a complex pole. Assume that you have a complex pole. When you have complex pole, you will not be knowing at what angle it departs. So the the indication or the initial angle at which it deviates from, assume that if you have one more somewhere here, if it goes like this, so then this is called as angle of, this is called as angle of departure. When you have complex force will end up with angle of departure. What angle of arrival? Supposing that you have something like this. So now we know that it actually breaks some area and then goes to this, The question is at what angle it arrives. At what angle it arrives is called as angle of arrival. Again, this is for complex zeros. You have angle of arrival. This is angle of arrival. Of course, we know in detail how we find angle of departure, angle of arrival, all those stuff we know. When do we use this is when you have a complex force, angle of departure, when you have a complex zero, angle of arrival. Okay, so that's it about the concepts of router and root locus. In the next video, we shall focus on uh, the Bode plot and log plots. Thank you.